And we're live. Yeah, yeah. Ho, ho, ho. All right, so yesterday we learned that the definite integral is kind of like a vector in the sense that it has a meaningful sign. Direction matters. If you ever integrate from left to right, then whenever your y values are positive, your integral is going to be positive. Whenever your y values are negative, your integral is going to be negative. But if you integrate it like it says here from right to left backwards, everything is backwards. Positive y values give you negatives. Negative y values give you positive, okay? And we can summarize that idea with this little equation. This is an identity. The integral from a to b, and again, when you read the definite integral, you always start with the bottom. I'm sorry, I put 2 down there. That should be from. From a to b of the function that is equal to the opposite of the integral from b to a. So what that allows you to do is if you ever see your intervals of integration, as they're called, and you don't like their order, no big deal. Just flip them, interchange them, and put a negative sign out front. If it's already negative, it becomes positive. If it's positive, it becomes negative. It just changes the sign. All right, so we can use then the definite integral to help us find area. But the definite integral itself, remember, is not always the area. It is always net accumulation. But if we know where the graph is negative, we could still use the definite integral to help us find area. We're just in charge of making that negative region positive so we don't get cancellation. All right, so here's another little identity that could be useful sometimes when we're evaluating definite integrals. Let's say you want to find the integral from a to b. I call this a travel agent identity. Right? Y'all know what a travel agent is? They're kind of not as prominent anymore because now we have websites where you can plan your own vacation. But travel agents are professionals that manage and book and plan your vacations, part of which is to obtain travel plans for you via airplanes, right? Flights. So if you're trying to fly from A to B, there's not always a direct flight, is there? Sometimes you have to fly to a connecting flight or a hub or something. So this is why I call it the travel agent problem. You want to fly from A to B. Well, there's not a direct flight, but you do have a flight that can connect you at C. So you could split up an integral into 2 separate intervals. You can integrate from A to C and then add it to the integral from C to B. So you're still going to ultimately get from A to B. You're just stopping at this intermediate value. Let me show you what that looks like with 2 different scenarios. Let's say you have this is A and this is B. And what you're after is the integral from A to B. So you're after, in this case, it's always easy to just put positive values up there. Let's say you're after the area of that. You can integrate from A to B if this function is f of x, and you can get the answer, no problem, right? But what if you can't do it directly? Well, you could pick a C value between A and B, like that. And you can integrate from A to C of that function. And what that looks like is this. Integrating from A to C gives you that. And then, of course, you add it to the integral from C to B of that same function. And that takes you, or gives you the rest of it, right? So the sum of 2 parts equals the whole. So that's the case when your connecting flight is between your original destination and your final destination. Is that how connecting flights always work? No, no. The hub is not always conveniently located. One time, I got my wife the gift of flight. I bought her wings, and they didn't work. So then I bought her a ticket on an airplane. She had never flown before, and so I wanted to take her down to the valley where I grew up with the Raspas and everything. I deliberately picked a flight that went from San Antonio all the way up to Dallas before it turned around and came all the way back down to like practically Mexico. And I did that on purpose so that we can maximize the flight time. See, I was thinking optimization back then. More airtime for the buck. More airtime for the buck. Yeah. And then we came back home because she didn't want to stay in the valley. She wasn't into the Raspas like I was. So let's see what that would look like. Let's say we're interested in finding again the integral from A to B. But now our connecting flight C is in Egypt somewhere, right? C, way over here. So the rest of this graph might look like that. All right, so this would be me flying then from A all the way to C. Way too far, right? But now, when I integrate from C to B, notice how am I integrating now if I'm going from C to B? I'm going from right to left. So even though it's above the x-axis, the sign of that integral will now be what? Negative, which means if I've gone too far, when I integrate from C to B, I am actually subtracting out exactly the amount by which I went too far, and I get back to the same integral with the same area. So anyway, there you go. True story of mine, helps you maybe remember this. This is the additive interval property, if you want to give it a name. So the C that you pick doesn't have to be between A and B. It could be anywhere as long as the function's defined there. Okay, so let's go ahead and look at example 5. We know the integral doesn't always give us the area, but we do know that we can use the integrals to help us find the area. So if we have this piecewise function, we want to write and evaluate an integral expression that gives us the area of the region. And we're doing it without the calculator, so we're not just going to take the absolute value of the whole thing like Indy suggested yesterday. All right, so step 1, when you have a piecewise function like this, easy to graph it. So here's -1 right there. There it is. To the left of -1, it's 3, which means it's going to graph as a what? Horizontal line. There it is, like that. Boom. With an open circle at -1. Then at -1, if you use direct substitution, when you plug it in, you get what? 3. So it actually picks up right where that one left off, and then it proceeds with the slope of -1. So it looks something like that. Where does it cross the x-axis? Can you figure that out just by looking at the equation? At 2, right? 2 minus x equals 0 when x is 2. All right, so we want to evaluate the integral then from -3 to 3. We want to find the area, sorry. It says find the area of the region from -3 to 3. So let's go ahead and set up our boundaries here. Here would be -3. And if I go a little bit further here, we'll call that 3. So what I want to do is determine the area of these regions because I'm interested in painting it. So knowing where this graph is positive and negative is kind of important. So here we can call it area equals. What would be the first integral that I could set up going from left to right? -3 to what? I can go to -1. Good. I can't go all the way to 2 because it's a different equation. So -1 is about as far as I can get to start. And if I do that, let's actually put the piece in there that we're going to be using. It'll be the integral of 3 with respect to x. Plus, now I'm picking up at -1, and I can integrate all the way up to where? 2. Now I'm on the same curve, but I have to stop at 2 because it changes to negative. So that's going to be the 2 minus x equation. So this right here kind of demonstrates already this principle right here. I want to integrate from -3 to 3, but I have a waypoint here at -1 because that's where the curve changed. I had to get on a different plane, in essence. All right, so now all I have to do to finish this up is to integrate from 2 to 3. So if I do that, if I just integrate from 2 to 3 of this 2 minus x equation, that's going to give me what type of number? It's going to give me a negative number. So we said there were 2 ways to make it positive. The first way is to do what out front? Subtract it. Good. When you subtract a negative number, it becomes positive. So that's one way to do it. Or, now notice you could just copy all this stuff here and paste it. The other way to do it is to add the integral from where to where? 3 to 2. Yeah. And that takes care of that property we learned yesterday. So anyway, that's an integral. Both of those are acceptable integrals that give you the area of the shaded region. Now, if you're going to find the area of the shaded region, you can evaluate those integrals without doing any Riemann sums or trapezoidal rules because, why? They're just rectangles and triangles. They're shapes for which you actually know how to find actual areas. So let's go ahead and do that. I'll just put either one of those equals. And you could go from, if you want to split it up like we did, the area from -3 to -1 is going to be width times height. What's the width from -3 to -1? 2, right? We don't care about the sign. 2 times the height, which is 3. So that takes care of this region. And then the next little region is a triangular what shape? Triangular triangle. Good, good. Which is 1/2 the base. That's a pretty good adjective for a triangle. You got to admit it. What's the base from -1 to 2? 3 times the height, which is also 3. Okay, moving right along. Plus, because we're finding area, here's where we can just say it's going to be plus. The base now is 1/2 the base, so that's 1/2 of 1 times the height. What's the height at 3? Yeah, -1 would be the y value, but we're going to just call it +1. So we can make it positive on our own when we're finding areas. And now if you simplify that, you get 6 plus 9/2 plus 1/2, so that's 10/2, which is also known as 5. And so 6 plus 5 is 11. So the area of the region is 11. Now what would the value be? We can use areas, by the way, also to help us find integrals. We can use integrals to help us find areas, and we can use areas to help us find integrals. So now let's kind of add on to this bonus question. What if I was interested in the integral from -3 to 3 of this function? I can use these 3 areas that I found to help me evaluate the, oh, I forgot my dx. That's what y'all are staring at. Sorry. I can use these 3 areas that I computed to now help me find the value of the definite integral. What would the first section be from -3 to -1? +6, right? Because it's above. I'm going from -3 to 3. That's from left to right. The next one would be also 9/2. What would the last term be, though, if I'm interested in the integral? Not +1/2, but -1/2. Yeah, that's the difference, again, between the integral and finding area. So that would be 6 plus 8/2, which is 4. It ends up being 10. So the net accumulation of this function from -3 to 3 was 10, but the area was 11. Okay? Or if you want to think about it in terms of a different thing, to net 10 units, we actually expended 11 units. Or we traveled 11 units to net 10 units. Okay, so there you go. Integrals can be used to find areas, and if you know the areas of the regions, you can use those to find integrals as well. You just have to assign them with the correct sign yourself. Pretty sweet. All right, so we talked about this yesterday. If you want to find an area of a function and you have a calculator at your disposal, there's no sense in taking all the time to split it up like this, although you could still do that. There's a faster way, we said yesterday. If you take the absolute value of the function first and then integrate it, that reflects all the negative values across the x-axis. And now you can just integrate from left to right. Is that the same as this, the absolute value from a to b of f of x dx? No, that's definitely not the same. So I'm going to put a not equal sign. The one on the right finds the net accumulation first, which already has potentially subtraction happening in it, and then you're taking the absolute value of your net accumulation. So that's not the same as making the function positive first so that there never will be cancellation, and then integrating straight across. So notice the big difference between them. This is the one that gives you the area, not the other one. Okay, example 6. We're going to practice this new theorem called area of a region on the calculator. It says use your calculator, so if you have one, that's great. I'll show you how to do it. Find the area of the region bounded by the graph of e to the x minus 3, the x-axis, and the vertical lines 0 and 3. Sketch and identify the region first. Okay. E to the x minus 3 is your parent function. The minus 3 moves the horizontal asymptote down to -3. So that's what it looks like. The y-intercept, if you want to know what it is, it's -2. So when you sketch it, it looks something like that. So that's the first curve. And now it's bounded by the x-axis. So here's another boundary. And then the vertical line's x equals 0. So that's the y-axis. And the line x equals 3. Is x equals 3 to the right or to the left of this x-intercept? Well, you should see, if you plug in a 3 here, e to the third is like 3 cubed. That's like 27 minus 3. That'd be some positive number. So for sure, you know that 3 is going to be somewhere over here. All right, so it says that we're trying to find the area, right? So let's identify the region. If you identify the right region, you have a better chance of finding the right area. We want the area of this pink region here. We want to paint it essentially. Can I just integrate straight across from 0 to 3? No, because if I do that, the little piece to start off with being below is going to subtract out from the area of the top one, and my area is going to be too small. So we don't want net accumulation here. I don't really need to find the x-intercept if I don't want to, because it's a calculator problem. So yeah, woohoo. So here's what we'll say. We'll say the area, squiggles or equals? Equals. Even though it's curved, because we're finding it on the calculator, which uses an excruciating number of rectangles, it's going to pretty much be exact. The area equals the integral from 0 to 3 of the absolute value of e to the x minus 3 dx. If this ends up being a calculator question, you would get one check, sometimes even two checks for your integral setup. They usually give you one check for the whole thing, or they'll split it up. They'll give you one for your integrand, which would be the absolute value of e to the x minus 3, and then another check for your intervals of integration from 0 to 3. Well, now that we have the setup, now we can go to the calculator. Not until you set it up first on your paper. So there's a logistic equation. By logistic, you don't have to do it from the graphing screen at all. If you're only going to do it one time, instead of putting e to the x minus 3 in your y equals, you could just, from your home screen, hit math what number? Math 9, right? And if you're in math print, it shows the definite integral. We're going from 0 to 3. And now to click to the right, there's two ways to get your absolute value. You can go to your shortcut menu again, which is alpha window. Notice number 1 is analog brake system. It also means absolute value. You can see that right there. So you could do that. You could do that, sure. Or the other way to get the absolute value is to recite your favorite math chant, which is math number 1. Yeah, it is number 1. Math number 1. What? Math number 1. Math. Click to the right to number, and there it is, the number 1. I don't care how you do it. Math number 1 or alpha window 1. That's weird to say that. All right, so there's the absolute values. Second ln, e to the x, click to the right, minus 3. And as soon as we type in an x right here, that means we're going to put an x right there. How does that look? Double check, triple check. It looks good. You hit enter, and boom. How many decimals do we report? 3. So you get 12.677. And that is even though you're rounding or truncating the 3 decimals, you don't have to put a squiggle. You only have to put a squiggle if it says estimate or approximate. That is correct to 3 decimals. Now let's go ahead and set it up. Let's say we didn't have the calculator. Now we need to know where the x-intercept is. So to find the x-intercept of f of x, we'll set e to the x minus 3 equal to 0. Separate the variables. You get e to the x equals 3. Take the natural log of both sides. This is what pre-cal is doing right now. And you get x equals the natural log of 3. So if I had to set it up by myself without a calculator, the area then would be the integral from 0 to the natural log of 3 of, and I could just say e to the x minus 3 instead of f of x. But that's going to give me what type of integral? Should be negative, because that's that little piece right there. This is the natural log of 3. So since I've already written my intervals of integration down, I'll just put a minus sign there. Or you can flip them and keep it positive. And then plus the integral of from the natural log of 3 to where? To 3. And because that one's already positive, I don't need to modify that to make it positive. Now there will be a time where you're going to be able to evaluate this without a calculator using the fundamental theorem of calculus, which is closely related to the antiderivative or the indefinite integral. Turns out if you can find the antiderivative of e to the x minus 3, you can evaluate that definite integral by hand and get the definite value without the calculator's help. But we're not quite there yet, okay? So that at least we know we could set it up like that. Now, if it was a calculator section, could you still set it up like this? Sure, and you could type that in and get the exact same answer. I'll prove it to you, because I know y'all are skeptical. negative, healthily skeptical, from 0 to the natural log of 3. And now I wish I had my function in y1, so I don't have to type it in every time. This is going to be a big bother. Minus 3. Okay, I'm done. That wasn't too bad. I spent more effort complaining about it than I did typing it in. Lesson learned. Oh no, I got to do it again. That's a huge bother. That's like twice the bother. I did not learn my lesson, did I? Nope. Words are meaningless. You got to show what you mean with actions. All right, so there's some motivating commentary while I'm typing it in. All right, so if I hit enter, I should get what? 12.6772159? 1. Now, it's finding it a little bit differently, believe it or not. The calculator is finding it a little bit differently. So if you don't get the 9-1 at the end, don't freak out. You got to find the enter button. I hit enter in space and nothing happened. There's the enter button. Oh, look at there. 12.67721, and then it diverges, 591 and 066. So your calculator, pretty impressive that it's able to do that quickly. With 3 decimal accuracy, it'll always be correct at 3 decimals. Can we tell which one here is more accurate? Not really, right? Not really. Once we learn how to evaluate it by hand, though, we can come back and compare and see, but we may be way past the moment by then. But they are the same to 3 decimals. Yes, yes? All right, so the moral of that story is when you have your calculator, it's a calculator question, don't waste your time splitting it up to help the calculator because you're not. You're just squandering your own time. Take the absolute value and then of the function and then integrate straight across. But when you don't have a calculator, you have to split it up to make every region positive, and then we'll be able to evaluate this after Christmas break. So anyway, comments or questions on that? Walk the walk. Okay. It says here to remember that definite integrals don't always give area, but they always give net accumulation. Okay. Here was a question that I adapted from an old actual multiple choice question on the AP exam. We've already seen that we can use integrals to help us find areas, and we've even seen areas help us find integrals. Here's another one where we're going to use the areas to help us find the integrals. It says the graph of f of x is shown below. Y'all see it? There it is. If a sub 1 and a sub 2 are both positive numbers that represents the areas of the shaded regions, then in terms of a sub 1 and a sub 2, write out these following integrals. Okay, so a sub 1, that's the area of that region, and a sub 2 is the positive number that represents the area of that region. Okay, so example A. We want to write an expression for the integral from -4 to -1. All right, so that's going to be what in terms of a sub 1 and a sub 2? It should be a sub 1, right? We anticipate that that answer will be a positive number because we're going from left to right, and the region is above the x-axis. So it is just a sub 1. All right, letter B. Now we want to write the integral from -1 to 4. It should be negative a sub 2. Excellent. Because we're going from left to right and the y values are negative, the integral should be negative. The magnitude will be a sub 2, but we have to make it negative ourselves. Good. Letter B, or C, sorry. The integral from 4 to -1. A sub positive 2 or positive a sub 2? Positive a sub 2, right. So just a sub 2. Reason being is a sub 2 is positive, and now we're going from right to left. So again, that's why it's important to always start reading the integral from the bottom. We're going from -4 to -1. That's backwards, so even though it's below, it should be positive. All right, now we're looking at the integral from -4 to 4. That's from left to right. A sub 1 minus a sub 2. Any objections? That is correct. First one all year without any objections. All right, you should be right more often. Okay, this is the actual question that showed up on the AP exam. It was a multiple choice question, and it just said in terms of a sub 1 and a sub 2, evaluate that. So I kind of broke it down to give us more practice. Okay, so first thing you want to notice is it's two integrals. That's like two entirely separate problems. So let's analyze the first term first. The integral from -4 to 4, we already said was a sub 1 minus a sub 2. Minus 2. So if you have a scalar multiple outside a definite integral, you can evaluate the definite integral and then multiply it by that scalar multiple out front. So you can write that as -2 bracket. And then what is the integral from -1 to 4? Negative a sub 2. Good. We found that individually earlier. And now we're going to simplify it because that wasn't the answer choice. So that's a sub 1 minus a sub 2. That becomes plus 2a sub 2. And now we have like terms. So when I combine them, I get a sub 1 plus a sub 2. And that was an answer choice. And that was the correct answer choice. So that's using areas to find integrals. You can use integrals to find areas. You have to know where it's positive and negative unless you have a calculator. And sometimes you could find areas of regions easier using geometric shapes, or you're handed areas of regions, and you can then use those by assigning them the correct SIGN sign. You can use those to help you evaluate a definite integral. All right, example 8. I stole this graph from a free response question from 2010. It was actually the last free response question on the test, and the score out of 9 was lower than I expected it to be. And some of my best students that year said that it tripped them up, and so I didn't understand why, so I just put it in the notes every year. Okay, it says the graph above is a function y equals f of x. So that is not the derivative of some function. That's not the second derivative. That is some function f of x. Got it. It's composed of 3 line segments. Okay, there's 1, 2, 3. So far, so good. And a semicircular semicircle. Yep. Call me Mr. Adjective. There it is. I see them. I see the semicircle in the 3 line segments. Find the equation of the line segment on the interval from 3 to 5 and use it to find the x-intercept of the line segment. Okay, so this line is kind of crossing in no man's land. There's actually a tick mark right there. This one crosses in no man's land between 2 tick marks. You don't want to just assume that it's going to be, let's see, 1, 2, 3, 4. You don't want to assume like it's 4.5 because it could be 4.5001. Then you got egg on your face, and that's hard to get off. So let's go ahead and just find it. To write the equation of a line, we need a point and a slope. Or if we don't have the point and the slope, 2 points will suffice, correct? Because we can find the slope. So I'm going to use this little space over here. Algebra 1 all over again. The slope is the difference quotient. This is a -1 down there. So I'll do -1 minus 3 all over 5 minus 3. Change in y over change in x. And that gives you -4 over 2, which is -2. Now I get to pick my favorite point of the two. Which one would you choose? Okay, you do the top one, I'll do the bottom one, and we'll compare answers. Okay? So the equation of the line, I'll use the bottom one, Collins using the top one. You get the y value, which is -1. I'm sorry, I just messed up. Y equals, first, the y value of -1 plus the slope -2 times x minus the x value of 5. So you could use the top point just as easily and you'll get the exact same answer. Now I want to know where that line crosses the x-axis. So what do I do with the equation to find that? Set x equal to 0 or y equal to 0? Yeah, I want y equal to 0. So at y equals 0, we get 0 equals -1. I'll go ahead and distribute minus 2x plus 10. So you get 2x equals 9. And x equals 9/2, also known as 4.5. Okay, well, at least now we know it's 4.5 instead of just wondering if our guess was correct. Part B, evaluate the integral from -7 to 0. The definite integral. So that's not area, right? That's the net accumulation from -7 all the way to 0. So now this is one of those times where, because these are made up of geometric shapes, I'm expected to find the actual value. So here's what you do, and this is a good free response technique. If you find the areas of regions, you can write the areas of the regions inside the regions, And then if those numbers show up in your calculations, it's enough to indicate your method to show how you're doing it. So this is going to be a triangle. It's 1/2 the base times the height. So if this is -2 and that's -7, that distance from -7 to -2 is 5 units. And then the height is 1. So 1/2 the base times the height is half of 5, which is either 5/2 or 2.5. So I'll write the 2.5 in there and I'll circle it. Now we have a fourth of a circle whose radius is what? 2. So the area of a circle is pi r squared. If we divide it by 4, we'll have it. So what's -2 squared? 4, right? So we get 4 pi fourths or pi. So I'll put pi in there and circle it. Now we have the areas. We can use those to help us find the integral. So as I go from -7 to 0, you don't have to show the additive integral property. You don't have to write the integral from -7 to -2 and then from -2 to 0. It's a lot easier if you just write your areas and then give them the correct sign. So what would the integral be of the first little triangle? Negative or positive 2.5? Negative. We're going from left to right and it's below, so that's -2.5. And then from plus pi. Good, plus pi. And you're done. That's it. All right, now the integral from 5 to -2. 5 to -2. Okay, I got to kind of see where that's going from. Here's 5 over here, and here's 2 right there. So I need to find the integral. Let me use a different color here for the shading. I need to find the integral going from 5 to 2. Now, the first thing that you should notice is when you integrate from 5 to 2, you're going from right to left. So everything should be the opposite sign of the integral. But I still have to find the areas. So this little triangle here is going to be 1/2 the base. Well, good thing we found the x-intercept because we need it. How far is it from 4.5 to 5? It's 0.5 or 1/2. So that's 1/2 the base times the height, which is 1. That's going to end up being 1/4 or 0.25, whatever you want to call it. So I'm going to write it in that little region and circle it. Now I've got another triangle. It's 1/2. I'm doing the calculations outside the triangle. The base is from 2 to 4.5, which is 2.5, right? Or 5/2, whatever you want to call it, times the height, which is the altitude. It is what? 3. So that ends up being 15/4. And you can leave it as 15/4. So if you leave that as 15/4, I would probably come back and write the 0.25 as 1/4. As long as you're consistent, it shouldn't really matter. All right, so now I'm ready to use those numbers. We're going from right to left. So the first number I'm writing down is what type of 1/4? Positive. Even though it's below, it's positive because we're going in reverse order. And then this region, 15/4, should be negative. So notice this is a way to indicate your method. You don't actually have to write out the integral equation like we did a little while ago and then evaluate it. As long as the numbers here line up with the numbers here, you're good. And of course, that ends up being -14/4, which is -7/2 to the flag.